Sorry. I was distracted there. You're here, right. Let's get started. We want to look at the phaser class. Now, the phaser has been around with us since Java 7. So if you've not heard of it, make sure that you actually are using something later than Java 7. You might be still using Java 5 or Java 6. I hope not. It's now the year 2019, and we should not be using Java 7 anymore. We should be at least on Java 11 or maybe 12. Let's have a look at what phase is all about. We're going to learn here the reasons for its existence, also what makes it different to older classes like Cyclic Barrier and CountDownLatch. If you don't follow everything, you're welcome to leave questions, but also this presentation is aimed at somebody who's already got a really good understanding of concurrency. Especially the demos, the coding demos are going to be of a fairly advanced nature. So if you get stuck on something, please do me a favor and grab my Mastering Threads course. That will give you a very good overview of how threading works. Also, if you are serious about Java, about your knowledge, you really should be on my Java Specialist newsletter. This is where some of the top minds in the Java world, well, they read it. I know, because they keep on sending me emails when I make mistakes, which is quite frequently. So please grab that, get onto that. It's a free newsletter. I send it out about once a month. And on that is lots of information. I've got hundreds of articles you can grab from there as well. Now, to understand phaser, I'm going to compare it to some of the other classes we have in Java. And the first one we're going to look at is the CountDownLatch. CountDownLatch is really easy to understand. You will understand that in like 2 seconds. Count down until you reach 0. Then the latch opens up and it stays open until you make another latch. So it's very, very simple. When you construct it, you have to specify what the count is. You can never count up again once you reach 0. In fact, you can't count up ever. So you would use this if, for example, you've got a bunch of resources you want to start, and once they've all started, then you want to activate and open up the gate. That's what you would use it for. So for example, here I've got some method which waits for the services to start. Now I've got a couple of services. I've got here a database service, and I've also got an email service which have to be started up. Now the CountDownLatch is great for that, but there's one thing which I don't like so much, which is that you have to worry about interrupted exception. That of course is not so cool to have to worry about that. And Phaser has a more modern way of working with interrupted exceptions. We'll see that in a moment. But besides that, this is a great class. The interface is also very simple. When you construct it, you specify what the count is going to be. You could say it's the number of permits you're going to have. And then you can await. So you can call await either without a timeout or with a timeout. And this will wait until the countdown reaches 0. Once the countdown is 0, it never goes up again. So if you want to have another CountDownLatch, you have to make another instance of the CountDownLatch. If you call await with a timeout and it doesn't come back within that time, then it simply comes back with false. So interface is very simple. Here's an animation which is based on what Victor Grazzi built, jconcurrent.com. It's almost exactly the same, except I changed the colors a bit and took away a couple of elements which I don't need for this demo. So if you want to look at play around with this, have a look at jconcurrent.com, and what he's got on there is almost exactly the same as what I've got over here. So we start with count equal to 4. This is the value of our CountDownLatch. And now when I call await, I can call await with lots of different threads, all waiting for the count to be 0. When I call countdown, it goes on to 3, 2, 1, and then 0, and it opens up. And now it's open, so in future any await or await timeout will come back immediately. We'll exit immediately, come back. Now, if I want to do this again, I have to make another CountDownLatch. I've got 2 threads waiting now. Again, I call countdown 3, 2, 1, 0, and now it's open. And again, after that, if I call await, it is open, so it just goes straight through. Make another CountDownLatch. Now, when I call await with a timeout, if I wait for too long, it won't open in time, so it simply returns false. If I count on quick enough, then it opens up and they all go through. Of course, depends on what the timeout is. So, as I said, this class is very, very easy to understand. There's not too much to it. The only problem is using it can get a bit tricky because of the because of the interrupted exception. And there's no way of, for example, saying await uninterruptibly. If you want to do that, you need to change the class. Another class that's similar to Phaser is Cyclic Barrier. This has also been with us since Java 5, so it's a very old class. The idea with Cyclic Barrier is that a whole bunch of threads might want to rendezvous at a specific point. And they've got 5 threads, and they want to, when everybody's at the same point, then they want to do something. And for example, you can actually have a runnable that gets executed when they all arrive at the same point. So here you would simply call await, and they all wait for others to get to the same place. Now, with the cyclic barrier, things get a bit messy when one of the threads times out waiting for the barrier. You then get a timeout exception which breaks the barrier. So any future threads which want to use the barrier simply get a barrier exception, barrier broken exception. That's not very good. So we'll have a look at how we can use it. And if you then want to use it again after the broken barrier, you have to reset the cyclic barrier. Here's the interface. You've got constructors taking either just the parties or also a runnable, which can be an action that must be done when everybody has arrived. It's a bit like your daily Scrum meeting. Await waits for the threads to arrive, but they must all arrive, and you can't change the number of parties at runtime, so that won't work. And if one of the threads causes a timeout exception, then you break the barrier, and after that you need to reset the barrier. Otherwise, any future threads will get a broken barrier exception. Again, I've got a demo based on Victor Grazi's work, and we start with having 4 outstanding parties, and I call await. Once we reach 0, then they all go through. So now if barrier is complete, they'll all go through. And as a side effect, the runnable, whatever runnable you've got, gets called. Now I've got some with timeout. I've got one thread with timeout. You get a timeout exception. And if you then try to use the barrier, you get a broken barrier exception over here, the broken barrier exception. I have to reset the barrier. I don't have to make a new instance, but I have to reset it. And after that, when I call await, then it works again, either with a timeout or without a timeout. And of course, if you have a timeout, you need to reach the barrier, or everybody must reach the rendezvous point within that timeout. Otherwise, you get a timeout exception. So this is the cyclic barrier. Again, fairly easy to use, except the interrupted exception keeps on hurting us. And in fact, here, you also have the broken barrier exception when one of them times out and doesn't reach it on time. The phaser is a mix of these. And it's more than just a mix, because first of all, you can change the number of parties that are registered over time. So you can add more registered parties. You can also deregister one party from the set. We also have a more modern approach to interrupted exception. So that's great. We can wait uninterruptibly if we want to. It's also more compatible with the fork join framework. I'll show you a demo of that a little bit later. It basically is a managed blocker, so that's really useful. The interface to Phaser is a bit more complicated than the cyclic barrier and the CountDownLatch. When you construct it, you can specify a parent phaser and the number of parties. Both of these parameters are optional. The parent phaser is used to arrange a tree of phasers, which can help to reduce contention. We can also change the number of registered parties on the fly, in comparison to a cyclic barrier, where it's fixed unto all eternity. With the phaser, we can signal other threads who are waiting that we have arrived. Now, arrive does exactly that. And arriveAndDeregister decreases the number of registered parties from the phaser by 1. So we can use these to signal, to say we've arrived. Similarly, we can wait with awaitAdvance for a specific phase, or awaitAdvanceInterruptibly, again for the specific phase, and also maybe specifying a timeout if we want to. Now the wait only waits. It doesn't signal anybody else that we have arrived. So and the normal awaitAdvance saves the interrupt for later. Now I'm going to show you some code that does exactly that, to show how you do that with, for example, the CountDownLatch. arriveAndAwaitAdvance also saves interrupt, and this is the method you would normally use if you want to rendezvous. This is a bit like the await method of the cyclic barrier, except that it saves interrupt. It makes it easier to use. And then lastly, we've got onAdvance, and this onAdvance we can override in order to decide if you want to, first of all, cancel the phaser, or terminate the phaser, or if we want to, for example, have an action that gets called, a bit like our runnable for the cyclic barrier. The one advantage of phase is that it knows what phase it's in compared to the cyclic barrier. Now, a bunch of other lifecycle methods I've left out. Let's look at a demo of this. Again, compliments of Victor Grazi. And I'll start with 4 registered parties. That's the initial phaser. And I now say arriveAndAwaitAdvance. This is actually quite similar to the way that the cyclic barrier would work. We've got 4 threads. They're all rendezvous and advance through. So that's the most common way of using it. So that's great. Now, let's look at something slightly different. If I've got, at the moment, I've got 4 registered parties. If I call register, I'm going to increase the number of registered parties over here. So now I've got 7, 8 parties registered. Now when I call await and arriveAndAwaitAdvance, I have to wait for 8 threads to get to the rendezvous point. So I can change the number of threads. If I want to decrease it, I actually have to call arriveAndDeregister. There's no deregister as such. You have to arriveAndDeregister at the same time. And now I've got, for example, only 1 thread. So of course, whenever I call arriveAndAwaitAdvance, it's there immediately. With 2 threads, the one will have to wait for the other one to arrive. All right, let's try registering. Let's make just 1 thread. So we've got 1 thread here, and then I've got a whole bunch of threads which are awaiting advance. This is uninterruptibly, and this is a little bit like the CountDownLatch. And then I call the arrive, which makes them all go through. But the difference is, the latch doesn't stay open. It's not a latch which stays open. The CountDownLatch stays open once you reach 0. So you actually can't use the phaser the way that you'd use a CountDownLatch. You can use the phaser the way you'd use a cyclic barrier, but not the way that you use a CountDownLatch. And that's basically all you can do. It also shows you how many phases you've got, so it keeps count of how far we've gone so far. But that's basically it. Most of the time you're going to have arriveAndAwaitAdvance being used for the number of phases, working like a cyclic barrier. Or if you want everybody, once off like a CountDownLatch, you can do that as well. But it won't work like the CountDownLatch generally. All right, and I think that's probably enough playing around. It's quite a nice little animation here. I love it. And actually, Victor has found bugs in the JDK with his animation. It was quite funny. He found one in stamped lock, for example. And I said to him, how did he find that? He said, no, just clicked around, clicked this, clicked that. And I said, wait, that is wrong. And found a bug. Right, so we've looked at some animations. We're now going to look at a demo. Now, I wrote this code, and I want to tell you a story with this code before I show you the code, because I'm busy recording, obviously, this talk. So my machine is a 6-core MacBook Pro. I know, I've got that keyboard. It's one of those. 6 cores, so it's 6 cores, so it's 12 hyperthreads. And at least 1 or 2 of them are busy with this recording. So I don't know how well this test is going to work whilst I'm recording. So we're going to try it out. But I want to tell you the story. When I was a kid, a young man, I used to print out invoices for my mother. She was a physiotherapist and she had pre-printed invoices, the doctor's receipts that you get. And I would print onto that her invoice for her customers. And so she was running out of invoices, and I wanted to create new invoices for her by simply photocopying her old invoice. And I went to the photocopy shop at the university where I was, and I tried to make a copy which was accurate to the millimeter. And I made the first copy, and it was slightly off, so I positioned it a bit differently. I made another copy, and again it was just slightly off, but in a different way. And I kept on trying to make photocopies. Now this was in the early 90s, probably about 91, 92. So it's a long time ago. And in those days, the tolerances on these photocopies wasn't that great. And the owner of the company walked over to me and said, "What are you doing?" And I said, "I'm trying to photocopy this piece of paper to make it as accurate as possible." And he said to me, "The tolerances on the photocopy machine are not as accurate as with the printing machine." And I didn't quite understand what he was saying. And I said, "Well, let me just try." And I kept on trying, burnt up some money trying to make photocopies, and I just didn't get it right. And eventually I gave up, and I said, "It can't be done, not with that technology." And it's a bit, what we're going to do today is going to be a bit like that, right? I don't know how accurate this is going to be. So what I'm trying to do is the following. I want to have a bunch of tasks that start work as close as possible together. Now, what I do is I take the number of hardware threads, which is nowadays runtime.getRuntime available processors on Java, and I divide that by 2, which gives me the physical cores of my machine, and I subtract 2 because I need some cores for doing this recording and other stuff. And I also need 1 thread for signaling the threads that they should start together. So on my machine, I'm going to have 4 threads that I want to start at the same time. So 4 tasks, actually. Tasks that I want to execute at the same time. Now, Java's not real time. So, well, at least the version I've got. So you really are very subject to weird effects like operating system scheduling, the garbage collector kicking in. So in order to shut up the garbage collector, we're going to use the epsilon GC, which doesn't do any garbage collection. So that will hopefully minimize the amount of interference we're going to have on our test. And we're going to code a whole bunch of different approaches, about 5, 6, 7 different approaches. And this is where I'm saying, if you can't follow everything, do me a favor, please, before you get upset with me, please have a look at my Mastering Threads course, because that will fill you in a lot of the blanks. All right, let's go to the IDE. So we start with a cojoined task. The cojoined task is a runnable, right? It's a runnable. And when you construct it, you pass in a joiner, right? And the joiner is what we're going to join in order to make sure that we're starting as close as possible to at the same time. So, and then the task that must be executed. So the joiner.run, this will wait until everybody arrives, hopefully, if it works properly. And then start time is the nano time. Now, I know that nano time is not necessarily very accurate, especially if I'm busy doing recording at the same time. So I don't know what's going to happen here. This could be completely wacko way off. And in fact, nano time is only guaranteed to be as accurate or as precise as system current time nanos. So it's only guaranteed to be in current time milliseconds. So it's only the resolution is only at least as good as that. And so the resolution might not be that great. The precision is nanoseconds, but the resolution might not be that great. And current time millis is also not necessarily going to have a resolution of milliseconds. It might be in tens or hundreds of milliseconds. So we'll just see what we get, right? It might be complete nonsense. It might be like my photocopy machine where I'm trying to make prints for my mother, but which just is not accurate enough. But we'll see if there's any difference between the various approaches. And then task.run runs the task. And of course, we can get the start timing in afterwards. So this is our co-join task. And we're going to have different implementations of the joiners and the signalers. Then the other thing we're going to show you is how the co-join task tester works. I'm going to, first of all, create a cached thread pool, which is going to have the number of threads that are available will stay pretty much constant. So once I've started up my test, the threads will just stick around until I shut down the pool right at the end of the test with shutdown. Also, I make sure that you have at least 4 cores for this test. So the parties is actually runtime available processes divided by 2 minus 2. So you need at least 4 cores to run this test. If you would like this code, please email me to, you probably are on my email already if you want this, heinz@javaspecialists.eu, and I'll be very happy to send it to you. I don't want to put it on GitHub because it's, well, people might draw the wrong conclusions with this code. I don't guarantee that it's correct. Okay, then the interesting method here is test. Now, test takes 2 runnables. One is a waiter, other is a signaler, or the waiter could also be called the joiner or the waiter, and then the signaler. It also has the total count and the max wait. Now, what the total is what I do is down here, I find out what is the smallest start time in nanotime, and then I find out how far was everybody away from that. So, for example, max accumulate will find the biggest distance from 0, well, from the smallest start time to the biggest start time. So, for example, if one starts at 200 nanoseconds, the other one at 2000 nanoseconds, then it's 1800 nanoseconds in between. Again, I don't know how accurate this is. I don't think it's very accurate, but we'll see what comes out at the end. And then also what I do is I first of all accumulate the maximum, so I can find out what is the maximum distance, and also add up all the differences together, so you can see what the difference is between them. And what we really would love to have a diff which is small, or a max diff which is small, and a total which is also as small as possible. So you don't have a lot of variation between the times. So when you say start with these tasks, they really start pretty much together. Right. That's what I'm doing. And then up here, what I do is I go from lot up to constant parties to make that many tasks. I make a co-join task, which is that task I showed you a moment ago. There's a co-join task. And the runnable that I'm going to do is I've got a shared value here, long adder total test. Now, the reason I'm doing that is I just want to do something. I want to do some work so that that code doesn't get optimized away. Right? So I want to make sure it doesn't get optimized away. And of course, don't forget that when you're doing, you probably realize that when I'm doing nanotime, it's actually a native method call. So again, you know, to actually measure stuff like this is difficult, or rather impossible. So I'm doing something which is impossible. And it probably won't work, especially because I'm recording at the same time. But let's try anyway. And then I convert this to an array of tasks. I like working with arrays. I then take these arrays. So I actually want to make all the tasks before I start, right? I then take these tasks, I submit them to my pool, and what comes back from submit is the future, and I'm going to put the futures into a list. So that's my list of futures. So I've got all my futures now. Once I've submitted all the tasks, I then signal to say, guys, we can start. So signal.run starts. And after I've started everything, then the futures, then I call future to make sure they're all complete before doing the next lot. So I make sure that all the tasks are finished before looking at the next. Now, I don't want to shut down the pool at this point. I want to rather keep it around for the next test. So it's the same 4 threads on my machine running test after test after test. All right. And I'm going to do quite a few of these tests. I'm going to do this like 20,000 times per run. So I'm going to submit these on my side, 4 tasks, signal, wait them all, then come back again, bring them back together again. And then print out what the max time was, what the total time was, also what the class is that I'm busy testing. And this I'm actually going to do 10 times. So I've got my test all, which has got all of the different mechanisms we're going to try. We're going to try using wait notify, using volatile spinning, a lot of different mechanisms, and then come back and see what the performance is. And we're going to do that 10 times, testing all of them. So a stream of all of these different cojoiners, and hopefully we'll see some difference between them. We'll see if it works or not. I'm going to run this exactly once. I'm not going to run it over and over again until I get the result that I want. And if the result's complete nonsense, then, well, I will give you that nonsense. All right. So none joiner would be the simplest. We do nothing, right? Which means the threads can just start. We're not going to do any waiting and signaling between them. So this is the simplest way of writing it. Just run wait and run signal, do nothing. All right. I'm going to show you another way which is also pretty simple, which is a volatile spin cojoiner. And here we're going to have a private volatile Boolean that needs to be Boolean. Ready equals false. If it needs to be volatile. If it's not volatile, this will not work. And here we're going to say while not ready, and signaler will say ready equals true. So this will work. And since Java 9, you could improve it slightly by saying over here, thread.on spin wait. Now, I don't think it doesn't seem to make a difference in my machine, but on some architectures, this actually will make a difference, make it a bit better. So this is a volatile spin cojoiner. So the waiter threads are sitting there spinning while not ready, going round and round and round, and then the signaler goes ready equals true, and they all go straight through. And of course, it could happen that one of the threads actually doesn't get scheduled before the signaler gets scheduled. So it would then see that it's ready already and just go straight through. It wouldn't go into the spin loop. So this is how the volatile spin cojoiner works. As I said, it's also fairly simple to understand. If you take out the volatile though, then it won't work because, well, it might not work because the threads might cache that value and not look at the shared field anymore. All right. So these two are the simple ones. Let's do the phase as well. That's also fairly simple. Here I'm going to make a private final phaser. And here, the number I'm going to use, the number of permits or the number of parties, is going to be the parties plus 1. I'm going to also have the signaler be part of the group of parties. The waiter is going to say phaser.arrive and awaitAdvance. So they're waiting for everybody to get to the same place, and then we're going to go and advance. And the signaler is going to say phaser.arriveAndDeregister to decrease the number. And that's it. That's all I need to do to write the phaser cojoiner. So that was quite easy. Let's do the next one, which is going to be, let's do the wait notify. Okay, this is getting a little bit more tricky, but it's still fairly easy. So here we're going to have a synchronized method, run waiter, and a synchronized method, run signaler. I need to wait for everybody to arrive. Now, when you're dealing with threading, you always have to be careful that you don't, because the thread which gets the task which gets scheduled last, the signaler, might actually be done before the first tasks are done. So you always have to have sort of some state machine in here. So let's make a simple perception of just having a private Boolean ready equals false to start with. And then inside here we're going to do something like while not ready, wait. Now I'm going to call wait, which is going to suspend the thread and let go of the lock. And then here I'm going to say ready equals true and notify everybody to wake up. So this would, it's almost correct, except that I have to now worry about the interrupted exception because, of course, wait throws interrupted exception. So I want to do this uninterruptibly, which means I need to do something along these lines. I need to say Boolean interrupted is thread dot, dot interrupted. Then I need to say if I get interrupted over here, in fact, let's put this catch into the while loop. And if we get interrupted, I'm going to say interrupted equals true. And before I exit, I need to say if I was interrupted, then I need to re-interrupt myself. So this sort of code is very common in the JDK. And it's pretty much what gets done when you say arrive and await advance. I know there's a lot more to see here, but somewhere in here, you're going to find when they return, over here somewhere, they're going to do blah, 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 and in there somewhere, I don't know exactly where, but somewhere in there, they're going to have a re-interrupting themselves, right? Interrupt is being called here, right? So there we go. If was interrupted and node is not interruptible, then we re-interrupt ourselves. So they do that somewhere inside the phaser class as well. But as I said, this is quite complicated. Oh, they do the spin wait. There we go. So they actually do spin wait inside there. We'll have a look at the moment at the performance difference between these various classes. All right, let's get back to the wait notify. So this wait notify all. So this also is correct. It would work as well. And now we're going to try which one's the next one? Let's try the condition. No, not this one. Let's try the single CountDownLatch cojoiner. This one's again fairly easy. We're going to, but it's getting more complicated. We're going to say private final CountDownLatch. Latch equals new CountDownLatch of size 1. The wait is all going to wait for that one latch, and the signaler is simply going to say latch.countdown. And then here again we need to do, of course, the whole thing with catching an interrupted exception. So try catch, and we need to actually do something along the lines of do a while true around that, and break out if we manage to call latch.await if we're successful there. If we get interrupted, we need to save that for later. So Boolean interrupted equals thread.interrupted, which also resets it to false. And then here we're going to say interrupted equals true. And before we exit from the method, we're going to say if thread or if interrupted is true, we want to do self interrupt. So we interrupt ourselves. I keep on putting extra semicolons at the end of my lines for some reason. So this is a CountDownLatch, and that's a single CountDownLatch cojoiner. The group CountDownLatch cojoiner is similar, but quite similar, not exactly the same. Here I'm going to have again the constants dot parties plus 1, right? And then before I call latch await, I'm going to say latch.countdown and then latch await. So it's actually making sure that everybody is at the same place before we move forward. Otherwise, what could happen is that one of the threads, if the signaler is sent too early, if the run signaler gets executed first, for example, then the other threads would all be, well, some of them would go through, some would not go through as quickly as others. So some might be waiting for longer. So to try and get things to be as close together as possible, we are doing it like this. All right. it gets slightly worse with the cyclic barrier. Let's just copy and paste this code, because some of the code I'm going to reuse. And the cyclic barrier looks something like this. We're going to have a cyclic barrier over here. Barrier equals new cyclic barrier. Again, constant parties plus 1, same as before. And here we're going to have barrier.await rather than countdown and all the other stuff. Barrier.await. Now, the interruptions we can keep like that, but there's another exception called a broken barrier exception. And in fact, you could also, the timeout exception happens with the wait with the timer. So you won't get a timeout exception here, but in theory, you could get a broken barrier exception. Well, you can't here because we're not actually timing out. So if you get that, we're going to simply throw a new illegal state exception, but we could also, in fact, throw an assertion error over here. And then the run signaler is also going to call barrier.await, just to signal as the last one that we are here. But with this one, I don't want to have a loop. I'm just going to do it a little bit simpler. If I get interrupted, I'm going to say thread.currentThread.interrupt and return. And if it's a broken barrier, I'm going to throw the illegal state exception. So it's very similar to the other one, but here I'm just going to throw an exception if the barrier is broken, and interruptions are just returned immediately. Now, what is bad is if you don't return from the method. Then you actually end up with a big mess. Now, we're almost there. 2 more I need to do. The first one is conditional await signal cojoiner. This is now using an uninterruptible wait. So I'm going to use a private final lock equals new reentrant lock. And a condition with that is ready equals lock.newCondition. And again, I need a Boolean. Ready equals false to start with. The waiter is now going to use the lock. So I'm going to say something like while not ready is ready dot await, and I can say uninterruptibly. So this is really good. Of course, I still have to wrap a try lock around that, and luckily IntelliJ has got that covered. And then the signaler, I need to say is ready, actually first I have to say ready equals true, and then is ready dot signal all. So wake them all up, and again, I need to wrap all this in lock.lock. So this is our condition await signal cojoiner. That's how you work with conditions and lock and condition and so on. And then the one last one, which is for the non-blocking guys, because we don't really want to be blocking, and that is acquire release spin cojoiner. Now I've got another tutorial on how to use var handles, but this basically will show you something about that. Again, we're going to have our private Boolean ready equals false to start with. And now what I want to do is I want to use acquire and release to set and get the values. Now acquire and release is good when you've got a single thread writing and lots of threads potentially reading. It can be faster. It can be in some cases a lot faster, depending on what you do. For this case, I don't think it'll make a difference, but in other cases, I have seen it make a massive difference between using this versus using volatile reads and writes. And the way to do it is to make a var handle, private static final var handle, and normally we call it by the same name but just in capitals of the field that we want to control with that. So we then have a static initializer block, and we say ready equals method handles dot lookup dot find var handle, the class which happens to be our class. The name is ready, and actually it completes it for us. And of course, this could throw an exception, potentially. So we need to put a try catch around that. And again, the default thing to do here is to catch reflect operation exception, and to then throw new error. So this is a bit involved, but there we go. We've now made the var handle. And I've got another tutorial that's only about var handles. So have a look at that one, part of this series. So to use this now, we can have very similar code to the way that wait notify worked. Here we're going to say while. Now to read the value using acquire release, we can say ready.getAcquire on this. All right. Now that actually gives a while not this. Now this actually expects a Boolean. And what comes back is actually a Boolean, but this is what we call a polymorphic signature, which means that even though it's not going to convert it to a Boolean object and return that. It's going to return an actual Boolean, but it returns object, and because it's a polymorphic signature, we can actually cast this to a Boolean. So we can say this is an actual fact a Boolean. So while ready.getAcquire, we can again say our thread.onSpinWait over here, and then the signaler is going to set it. So we're going to say ready.set release this comma true, so make it true. So this is how the var handles work, and this means I can still have just a normal Boolean. I don't have to use an atomic Boolean, for example. I could also do this with atomic Booleans as well if I wanted to, but then it's a different place in memory, so one less indirection doing it like this. Okay, so if I've done everything, I think I've done all of them now. Let me just quickly check that I haven't left one out. And of course, you probably agree that the easiest one is the phaser. Well, of the ones that actually work, because none doesn't actually work. But this is the easiest one to use. Second easiest would be the volatile one. And the other ones are all kind of complicated, especially because you have to worry about interrupted exceptions. So let's run the test and see how well it works. I'm going to not re-record this. It's just a single record. And I'm curious to see how well this works. I obviously have run this many times without recording. You can see here that this is running with the epsilon GC, and okay, my results are not as good as without the recording, but they're not that far off. Okay, they're not that far off. I'll let it run to the end, and then we'll look at the results together. So, for example, for the phaser without recording at the same time, I was getting about 4 or 5 million, and it was really consistent. With the recording on, it's getting to like 11, 12, 13 million, which is not as good, but it's still not bad. Still not that bad. Now, what epsilon GC does is it just allocates memory until there's none left, and then it fails. So if I ran this for very long, it would just crash. But it allocated about 3 gigabytes of memory, and then I was finished, so it stopped. And it's allocating 51 megabytes a second, which is not that much. It's really, the allocation rate's not that high. I found with epsilon that high allocation rate code tends to be slower than if you don't have a garbage collector. High allocation rate where you're throwing away the objects again, in other words. Because with the normal, when you take epsilon GC, of course, underneath it, there's real hardware. And it's got to map it onto this massive chunk of hardware. I've given it 16 gigabytes of memory, which is half my RAM in my machine. So whereas if I take, for example, the throughput collector, if it's a high allocation rate, it can simply allocate it inside the Eden space and throw it away really quickly again. So with high allocation rates, typically I find epsilon to not be as fast as other mechanisms, which is sort of a bit surprising. All right. So what I find here is, as I see, these numbers fluctuate really big, really widely, as you would expect to have on a busy system where I'm busy recording as well. And here you've got if you don't do anything, like the maximum value was 159,000, 159 microseconds basically, which is quite a big number. And if you add them all up together, it's 295 milliseconds in total variance between all the different starts. What is funny is that it's actually not as bad as the other ones. So and this is consistent with when I ran it without the recording on, is that you actually found that that if you don't do anything, it tends to start quite consistently. Now the other one, which we have as await notifier, here the total is normally quite high, so sort of 500 milliseconds of total variance over the entire run. Half a second, so here's half a second variance again. For the condition await is not much different to that one. It's very similar actually. The CountDownLatch again is very similar. Interestingly, the group CountDownLatch actually had a bigger variance than the other one. And this, I've seen this also in the normal test without all the other noise around. This isn't like me trying to photocopy my mother's invoices. The Cyclic Barrier is consistently bad, like worse than anything else. And I've seen that with all of the tests that I've run, that's actually had the biggest variance. The volatile spin, I am not sure why it's so bad. I mean, it's better than the other ones. Like, it's better than the await notify, it's better than the condition and all the other ones, but it should be better. And I think it's part of that is something to do with my test, because I have tested this and I have gotten better results than the volatile spin. But the best consistently is the phaser. If you look at the total, especially the total, it's like 14.9 million, 15 million, 13.8 million, total variance 11 million. And as I said, when I was running it without the recording on, I was consistently getting 5 million and below in total variance. Also, the max normally is quite low. I mean, here it's not so low, it's 38 thousandths. I mean, that is, here it's the best, 38 thousandths, better than all the others. But it shows you that the phaser with this little test is, number one, the easiest way to write it, okay, except for doing nothing, and it's actually the most, it gives the best results, which is really pretty cool. Now, luckily I didn't have to write this code, because as you saw, this class is kind of complex, you know, like just to do arrive is like, whoa, man, my head hurts looking at this code. Do register, it's really complicated. Reconcile state, I don't know, each of the methods is really long and complicated. I mean, this is more than 1,000 lines for something which should be fairly simple. They also, of course, use var handlers as well. And then if you compare this, for example, just in bulk, it's like 1,100 lines to the CountDownLatch should be lot shorter. This is like a third of that, of which probably most of it is just comments. There's hardly anything in here. This is very simple. I mean, I could write this myself very easily. The phaser is far more difficult to get right. So there we go. Now, what's interesting is I mentioned that the phaser is compatible with ManagedBlocker. Well, there's something new coming called fibers, and I'll get back to that in a moment. As I said before I started my demo, if I lost you anywhere, I hope I didn't, but if I did, please have a look at my Mastering Threads course. It will teach you everything you need to know about threading. Well, not everything, but it's a good start. It's a great start. The phaser also counts the current phase that we're in, and we can have an action being called whenever we go past one phase. So we can have onAdvance being overridden, and inside that we can also decide to cancel. So if we return false, I believe, then we want to cancel. Returning false is cancel, returning true means continue. I think, I'm not exactly sure. I can never remember this way around. So I wrote this demo, and what the demo does is it shows a bunch of buttons. So it's, swing buttons. And it shows 20 buttons in my demo. And the buttons all change color to some random color. And then they sleep for between half a second and 3 seconds. So we'll sleep for some time. And then we make a beep. And we sleep for 2 seconds. We first change the color back to the original color. We then beep, and then we sleep for 2 seconds. So once everybody's arrived, then we do this whole thing again. And we do it for 3 times, and then we terminate. Once the phase is terminated, then we exit. So here's the demo. And I wrote this, and then Victor Gratz used it also in his concurrent animated tutorial. But it originates from me. So let's start. You can see the buttons all back to normal. 2-second wait. And then between half a second and 3 seconds, they all change back. Again, 2-second wait, and once more. There we go. I've often spoken about phaser at conferences, phaser and stamped lock and var handles and things like that. And I've never had the opportunity to really give it a lot of time. As you see, it's a very complicated piece of machinery. And one of the things they've got in there are tiers. You can have trees of phases. And the purpose of this is to reduce contention. Now, it's a little bit complicated to understand. And I'm going to show you a little example, which will make it a bit easier, I think. So a parent doesn't know what the children has in terms of what's inside the child. So when you add a child, then the parent's number of parties increases by 1, but only if the child's registered parties is also bigger than 0. So if the child doesn't have any parties, then the parent's number does not increase by 1. So the parent's number doesn't increase by the number of registered parties the child has. It just increases by 1 if the child has any registered parties. It's always 1 more. Now, once a child arrives, parties equals 0, then 1 party automatically arrives at the parent. Right? That's why and because of that, we only increase it by 1. So that increases by 1. So when you call arriveAndAwaitAdvance, we have to wait for all the parties in the tree to arrive. And so the parties in the current phaser and in the parent have to arrive at the same before you can make any forward progress. Here's an example. I've got a root phaser of size 3, so 3 parties for this phaser. I then make C1 with 4 parties. And so if you print out what's inside C1, it's going to say there are 4 parties inside. C2 is going to be the 5 parties, and C3 has as parent C2 and has no parties at all. Now if I print out C3 has no parties, you're going to see party equals 0. That's C3. If I print out C2, it's got 5 parties. Even though it's got C3 inside C2, because there are no parties inside C2, it doesn't add 1 to the parties of C2. C1 is just 4 parties, and then root is 3 plus 1 for the C1 plus another 1 for C2. So there you can build up this tree, have tiered phases. Here it is again. Root parties equals 3. I add C1 with 4 parties, and this increases the number of parties to 4 inside the root. If I then have C2 added as well, this has parties equals 3, and again this increases the number of parties inside my root phaser. And then I've got C3 with party 0. This does not increase the number of parties because the parties in C3 are equal to 0. The purpose of all of this is to be able to build phases with the minimum amount of contention. And contention is a problem because contention can cause our threads to be blocked and to not make forward progress. So this way we can have threads looking at different parts of one big phaser instance. Typically when you construct a fork join pool, you do not specify the maximum number of threads. Now, I know in Java, I think Java 9, you can actually specify that, but most don't. So most of the time you just specify, I want to have a parallelism of, for example, 13 threads or 12 threads or 15 threads. And Java then tries to maintain it at that level. Now what happens if one of the threads blocks? Well, If one of the threads blocks, then you actually are decreasing the number of active threads inside your pool. Things tend to work okay-ish because in Java, they by default use the number of hardware threads as a basis for the number of threads inside your pool. So in my machine that I'm using here, I've got 6 hardware cores, and each of them has 2 hyperthreads. So when Java asks the operating system, how many cores do you have, how many processors do you have, it sort of lies a bit. It says that it's got 12, because it asks the hardware, and the hardware says it's got 12. Of course, it's got a lot more, because it also says GPUs. But the normal processors, it's really got 6. And it's got hyperthreading on those 6. So that's why it says 12. And because we actually have more threads in the default thread pool than you've got cores, things tend to work still sort of okay, even if 1 or 2 threads blocks a little bit. So as you don't have too many threads blocking, you tend to be okay. Now there's, as I mentioned very briefly before, that there's a new project called Project Loom, where they are going to give us fibers, and the fibers are all executed on the common fork join pool and the current implementation of the fibers. So they're all running on the common fork join pool, and when a thread blocks, either with the CountDownLatch or Cyclic Barrier, or with the re-entered lock, it doesn't work with wait notify, but any of the other ones, or even reading files. Then the task can be swapped out. Another task can be swapped in, so that you can share the number of threads between all the fibers which could be running at the same time. So this is a new technology which is coming, hopefully, maybe by the time you listen to this, it is already there. Hopefully it will be there soon. Here's an example. What I'm doing here is I'm creating 100 different actions. And these actions are going to be run at the same time using Phaser. And so here's my fork join pool, and I've got a phaser of 100 actions or 100 tasks, threads that need to be waited, need to wait at the same time. And when I call arriveAndAwaitAdvance, it actually will create additional threads to pick up the slack, so that you end up still being able to complete this, even though I only have 12 hardware threads. And when I've got 12 hardware threads, then they're going to be by default 12 threads inside this fork join pool. We'll make a new fork join pool. And when you run this code, you will see that there are 100 threads being constructed, and it still works. This still works. None of the other mechanisms would work. I wouldn't say none, but yeah, probably none of them would work. But this one works, and it works really well. So that's an example where ManagedBlocker is used. Another one is also with the completable futures. They also use this ManagedBlocker mechanism. To summarize, we've come to the end of the phaser, and I started by comparing it to some of the other mechanisms out there, like the CountDownLatch, which is basically counts down to 0. Once you reach 0, then bingo, you're done. The Cyclic Barrier, where we all rendezvous at a specific point, and if somebody doesn't come within a timeout, then you break the barrier, and you can't. For those first two, you can't change the numbers. If you want to do another CountDownLatch, you can't reset it. You have to create another instance of the CountDownLatch. And then the phaser is more flexible. It also has a better mechanism for working with interrupts, and it works. It plays nicely with fork join pool and / parallel streams / all the other mechanisms you have got out there that you might want to use. I'm sure you want to have more resources, more information. If you watch this far, definitely you want more information. If you haven't subscribed yet to Java Specialist newsletter, please do. It's not this newsletter by the Java Specialist. I do Java Specialist stuff, but it's for Java Specialists. So it's for people who work with Java. So if you're working with Java or Android, you want to be on this newsletter. It's the thing to know, the thing to use. I also mentioned I've got this online bootcamp for Java Specialists. It's advanced Java lessons like you won't find anywhere else. You will not find the volume or the quality of this training anywhere else in the Java world, in the world, actually. It's the only one like this. And I always have people getting on it and they say, wow, I've been looking for this for a very long time. There's nothing else like this. I've got loads and loads of feedback from my students. If you're interested in concurrency, get onto the concurrency interest mailing list. It's also a very good one. There's a link for you there. And if you have any questions or comments, please email me, heinz@javaspecialist.eu. Always happy to hear from you. I've also got a Twitter handle, and I accept messages from anybody. So just don't send me like, please do my homework, because that I will not do that for you, because you'll get it wrong. So that's it. Thank you very much for watching, and I hope that you learned something about this very seldomly known, unknown, hardly known. I don't know how to say that. English is not really my strong point. Java is stronger than my English. Little class called Phaser. Thanks so much for watching.